Okay, so the person who is responsible for like introducing speakers is Dr. Gaussian Jim. So he would just give you a formal introduction before you go ahead.
Okay, perfect. Maybe just a quick question. So about timing, like what should I aim for?
It's up about like 50 plus 10 minutes questions.
Yeah.
But you could also go to an hour because I suppose people would just ask questions during the talk.
Yes.
Unless you hope to put.
No,
okay.
Not at all. Please interrupt.
Okay, good. Okay, so I would just let maybe Guojin, you could start like your. Okay, good. Thanks.
Okay, thank you. It is an honor to invite Simon Apers to give us a talk on his recent work, the quadratic speedup for spatial search by continuous time quantum walk. He is currently a research scientist at IRIF and focuses on quantum algorithms and theoretical computer science, such as random walk, graph theory, and combinatorial optimizations. Before that, he finished his PhD degree at Gand University, and in 2018, he did the first postdoctoral jointly between IRIA and CWI, and worked with Anthony Leveria on quantum error correction. And he also worked with DeWolf on the project of quantum algorithms for web problems. After that, he did a second postdoctoral jointly between CWI and the University Libre de Bruxelles, and work more on quantum walks. So let's welcome Apers again.
Okay, thank you. Okay, so yeah, so I'll be talking about this work. As I said before, let me put a timer. Please interrupt at any time. Like I'll be very happy to take any questions. Because I had to puzzle a bit with how to approach this talk. Like we build on a number of formal results from other papers that I didn't want to go through completely, so I decided to focus on certain things. But I can always give more explanation about other parts. So feel free to ask. So this is joint work with Shantanu Chakraborty, Leonardo Novo, and Jeremy Roland, which we started when I was at ULB in Brussels. And it'll be in TQC in July, I guess. Okay. So, okay, let me first try to phrase the main result. But in order to phrase the main result, I'm going to introduce a couple of things. So first of all, throughout this talk, you can think about graphs as being simple, undirected, unweighted graphs, which typically I'll denote by a sort of a blob like this, which is really a thing of consisting of vertices and edges between the vertices. And on this graph, we'll consider an object first, which is called a continuous time random walk, and then afterwards we'll go to continuous time quantum walks. And we describe a continuous time random walk basically by a random variable x sub t, where t is a real non-negative time index, and this will always be part of the vertex set. So basically, the way you can imagine that is that it is a continuous time random walk, but not a continuous space. So it basically jumps, like let's say it starts from here, it jumps from vertex to vertex, where the time it takes to make a jump is like a Poisson process in some sense. And then it ends, let's say, xt here. Okay, so this continuous time random is not fully determined by the graph. In fact, what you should do is you should specify things called transition rates, which I'll call qxy, which is the transition rate to go from x to y, which is a non-negative number for all x different from y. And based on these transition rates, we can define the transition kernel q, which is as as it's off diagonals, basically what you would expect, Q12, Q13 until Q1n. And then on the diagonal, you basically get, so it's a bit like a Laplacian, you basically get minus the sum of the off diagonals. Okay, and this goes on like that. So basically, the kernel Q has rows summing to 0. And while these off diagonals should not necessarily sum to 1, if they do, then this actually corresponds to a special kernel of the form, right, so this is an example, Q equal to identity, so this should be minus identity plus P, where P is a discrete time random walk transition matrix. Right, so this kind of fits the form where now the transition rates are basically given by the off diagonal elements of the random walk transition matrix. And this particular form of kernel that we'll be considering throughout this talk as well. So again, here P is just a stochastic random walk transition matrix. Okay, in this kernel Q lets us define how basically the probability distribution of the random walk, the continuous time random walk evolves. Namely, if we start from x0 distributed according to some distribution p0, then xt would be distributed according to some distribution pt, where pt takes the very simple form, pt is equal to p0 times the exponential of the kernel times t. Okay, and this is kind of an important form here. And then you can also take a second to appreciate that it really looks a lot like how you would describe Hamiltonian evolution of a quantum system, but this is how the sort of the classical stochastic system evolves. And in fact, we'll be using this sort of analogy between this classical evolution and the Hamiltonian evolution. Now, if G is irreducible, it's kind of an elementary fact, but I'll state it. If G is irreducible, then there exists a distribution pi such that pt, as t goes to infinity, so basically the distribution of xt as t goes to infinity converges to this unique distribution pi, irrespective of the initial distribution. So you can imagine that on this graph, you can start from any point, and after a number of sufficiently large number of steps, basically the distribution will be will have forgotten its initial state. That will be approximately pi. And this is, of course, what we call the stationary distribution. Okay, and also this one plays an important role. And then finally, the final concept on the classical side we have to introduce is the hitting time. And the hitting time can be defined in multiple ways, but the specific hitting time that we're interested in is the following. So we take a subset of the vertices, which you can imagine is some blob like this, and these are the marked elements. So when I say marked elements, you can think about, like in an abstract search, like Grover search, you have a set of marked elements, and all the other elements are unmarked. So we denote these by M. And then we can define the following thing. Like, let's say that we start from some initial state x0, which is distributed, which is picked from the stationary distribution. And then we kind of let it evolve for a bit, as we saw before. It looks a bit like this. It makes these sort of random jumps, and at some point, it'll jump inside the set, right? So we'll have at some point that x tau is in M, and this time, like this is a random variable. This is one of the things that we call the hitting time, and we define it as follows: tau of M is basically the smallest time such that xt is in M, given that x0 is distributed according to pi. So we start from the stationary, and we have the stopping rule. It stops when we hit a marked element. And now this is a random variable we call the hitting time, but with some abuse of terminology, we typically also call the expectation of this random variable, which is no longer a random variable, it's just a number, is what we call the actual hitting time of set M. And this here is kind of the key quantity here. So this is a quantity that depends only on the random walk transition matrix and the set of marked elements, right? Because recall that we always assume we start from the stationary distribution pi. So this does not depend on the specific initial state. Okay, and this quantity is wildly varying for very different graphs. It can be very small, it can be very large. It all depends on somehow like the topology of the graph or how the graph is structured, how many marked elements there are, where they are, and so on and so on. It's kind of an interesting quantity, and it quantifies sort of the complexity of a problem that we call spatial search, which is you start from a vertex in the graph. You will assume that this initial vertex is distributed according to the stationary, and we take a number of steps until we basically sort of, it's a bit like a brute force thing, like we just walk and walk and walk until we find a marked element. Like how many steps do we have to take, or what's the time for a continuous time, random walk, to evolve before we're in this set of marked elements. Slightly more specifically, what we can say by using this definition of the hitting time, we can say the following. That is, if we start from the stationary distribution pi, which I'll expand as follows, just pi x ex, where ex is just the basis vector on corresponding to node x. So if we start from this distribution, then we can find a marked element in M by running a continuous time random walk, as I defined before, for time which scales as order of the hitting time of M. So I put order because it kind of depends on how you want to define find, right? This is a probabilistic algorithm. So do you want to say, what's the expected time to run, or do you want to say what's the time to run before I find with constant probability or something like that? This is kind of your pick. So I just put a big O here to cover all that. So this follows just from the definition of the hitting time, basically. And so what our kind of main result is here. Our main result is that we have this kind of a quantum version of this classical algorithm. Namely, what we prove is that if we start from the quantum encoding of this stationary distribution, which is just like the naive thing that you would do, you just put square roots here. So that if you measure the state, you would get a stationary distribution. Then we can find a marked element in M by running now a continuous time quantum walk, which I'll specify in a little bit. Right? So we run a continuous time quantum walk, and we run it for time which is basically up to polylog factors quadratically smaller, like square root of the hitting time. Okay. And this is like the sort of main thing that we wanted to prove, and we did. And while proving this, we kind of ran into some what we think are interesting techniques that I'll try to highlight a little bit. So this is our main result. If there's any questions at this point, please feel free to ask.
So basically, this OTL that means that you hide some log terms in that, right?
Yes. Yeah.
Okay. Okay. Good. Thanks.
Just
to, okay.
Yeah. Like typically, I think if we know what the hitting time would be, then we probably wouldn't have log factors, but we don't. And so typically you have to do some sort of binary search, and then you get these log factors, right? Okay.
Sorry. Are there results on discrete heating time similar to that? Similar to what you have for the continuous quantum walk?
Yes. Yes. Okay. Exactly. This is exactly what I wrote down a little bit lower.
Okay. Good.
So, exactly. So I mean, this should have ringed the bell with some people. So in fact, this is a continuous time analog of a discrete time quantum walk algorithm from stock 21 by Ambanis, Gillian, Jeffrey, and Kokanis. So they proved the same result, and with that, they kind of finished in fact, rather long line of research on like quantum walk search problems in a discrete time setting. Right, this all started with like Ambainis's quantum walk algorithm for element distinctness, and then there was Seghedi's work. Then there was work by people like Frédéric Magnès, Jérémy Roland, and others, and so on. And it's like it really took many steps to basically get to this full result. Like this last piece of the puzzle was really like, what if you have many marked elements? This was somehow not covered by previous algorithms, and they kind of resolved this last piece of the puzzle. And we strongly built on these results. And so now I should justify a little bit why it doesn't directly follow from basically their result. And it does to some extent, but it is still kind of a self-standing question because continuous time quantum walks have really been behaving rather different from discrete time quantum walks. And I'll explain that a little bit. So there is this discrete time result by Ambainis et al. But there's some main hurdles to like transfer this to the continuous time quantum walk setting. Okay. Now, one of these hurdles is that I mean, this is in fact also something that you have with discrete time, but you have it in particular with continuous time quantum walks. That there is like a variety of continuous time quantum walks. It's not clear how do we define a continuous time quantum walk, and what can we do with what type of continuous time quantum walk. Like one of the earliest sort of continuous time quantum walk search algorithms was one by Childs and Goldstone from 2004. And what they did is they considered like what I call the simple quantum walk Hamiltonian. So that means, okay, so your quantum walk Hamiltonian is fully determined by the Hamiltonian, right? So I'll typically just talk about the Hamiltonian, and then the quantum walk corresponds to just integrating the Hamiltonian evolution with this Hamiltonian. So they take a very simple one where the Hamiltonian is just, okay, identity minus P, which I mentioned before, as you can think about it as sort of the continuous time random walk transition kernel. And now why do I call this simple? Because I will come back to this, but for those familiar, there is no such thing as a what people call a coin. Like typically discrete time quantum walk results, like starting from Ambainis and Seghedi and so on, have shown that typically a discrete time quantum walk needs this extra coin degree of freedom, which is, you know, significantly increases the state space with respect to classical random walk algorithms. But so they consider the simple quantum walk Hamiltonian, which I imagine is, you know, the sort of straightforward thing to do. And then, you know, you have obviously what you do, you just evolve some initial psi 0, which could be, you know, this quantum encoding of pi, but it could be any other state. And you basically do Hamiltonian evolution. Right? You do psi t, which takes it from e to the minus I t q psi 0. And so what they showed is that if you do a slight modification, so let me just put a prime here, namely, you sort of do not do anything at the marked elements. Then they showed that in fact you can use this quantum walk to find a quadratic speedup for spatial search on things like high-dimensional lattices, the complete graph, the hypercube, and there's another range of graphs. But it's also clear that it doesn't seem to work for general graphs. In fact, my co-authors on this paper have a work in which they try to probe a bit the limits of the sort of simple quantum walk Hamiltonian. But I think it's not completely clear yet. But it does seem clear that using this quantum walk, you cannot get this quadratic speedup on general graphs, which is really what we're after. So what we do instead is we consider an alternative quantum walk Hamiltonian, which is called this, which was first described in the Soma-Ortiz paper from 2010, and they do use a coined quantum walk Hamiltonian. So it is coined, and that makes the sort of continuous time quantum walk now a bit similar to the typical canonical discrete time Seghedi quantum walk. And I chose not to specify precisely how HP is, or how HP is defined. Those familiar with the Szegedi quantum walk, it is a bit similar, but there's some twists. Like, of course, it has to be Hamiltonian and so on. But I'll just state the main property, and this is also the only thing that we'll use. So it is defined such that you apply it on. So, like I said, it's a coined quantum walk. So you apply it on this, let's say psi 0, but there's like an extra coin register, which typically you can think about as basically a second copy of the vertex set. So this quantum walk takes place on a slightly larger state space. But what the gist is here is that if you apply this Hamiltonian twice, like HP squared, on this larger state space, then you basically leave the second register invariant. It plays a role, but it doesn't show up in this particular equation. And you just apply on the first register, which is like the main register of interest, you just apply identity minus p squared, which is like a sort of transition kernel of a continuous time random walk. So it's identity minus p squared instead of identity minus p. But if p is a random walk transition matrix, and so is p squared, and so identity minus p squared is equally valid as a transition matrix. Sorry, as a transition kernel. So this is the main property that we'll use. And then again, quantum walk evolution is now on the slightly larger state space. So if you evolve according to this HP, then well, the specific equation shows that if you apply HP squared, then it just like works on the first register. In general, you will get like a coupling between the two registers. And so like this e to the minus ITHP on psi 0, 0, you can no longer kind of decouple. Like it'll basically be on the full doubled state space or coined state space. And this particular equation here is really kind of what we use. Is like the gist of the quantum walk. Okay. Then I'll go to this second hurdle where we basically put the main technical work. Is that Ambani, Skilly, and Jeffrey Cocanis in their discrete time quantum walk results from 21, they build on a discrete time technique called the quantum fast forwarding, which I described in an earlier paper with Alessa Let in 19, where basically, I mean, the kind of idea is that you can implement the random walk transition matrix p to the power t using something like, again, I'm not going to hide some stuff, square root t quantum walk steps. And this is in fact discrete time quantum walk steps. So this is a result in itself, but it's an intrinsically discrete time result. And in some sense, you feel like, okay, you're kind of, getting a quadratic improvement in the time parameter here. And this is also really what's going on in this quantum walk search algorithm. And that's also how Ambani et al. Used it to prove their result. And we asked the question, like, is there a continuous analog of this? And in fact, there is, and what I think is very nice is that in some sense it seems even more natural, like the continuous time analog. So throughout, I'll try to motivate a little bit why we also think that this continuous time setting is in fact relevant or useful. One of them is that some people like to argue that implementing a continuous time evolution might be more natural on a quantum computer. Others disagree, but this, I'll leave that in the open. But another thing which I really like about this continuous analog is that this fast forwarding technique really seems to pop up much more naturally. So I'll try to convey that message a little bit. So this will be the main technique that I'll devote the rest of the talk to. And it relates to something called a quantum Gaussian filter. But maybe before I go into that, like, are there any questions about what I said so far?
No, I think that's clear.
Okay, that's perfect.
Thank you.
Hello. Sorry. May I ask a question?
Yes.
So I'm not fully understand the first hurdle. When you say the 1 minus p, the p is specific to some projection, and why, right? And then what's the
You mean this thing here?
Yeah, yes.
So P is not a projector, but it's like the random walk transition matrix.
Oh, okay. Sorry.
Yes, so like you can think about it, like say for a regular graph, like you don't even think about, you can just think about it as the adjacency matrix, divided by the degree if you have a deregular graph. So it's a bit than that, then HP would just be the Laplacian of the graph, and it's kind of a logical Hermitian operator associated to a graph, so it makes a lot of sense to define a quantum walk using this Hamiltonian. That's what they did.
Then why is the hurdle? What was the hurdle you mean?
Okay, so the hurdle is that basically there's this variety of continuous time quantum walks, and this was like a very natural candidate to try to prove the result that we did, but it's kind of clear that this one does not work. So we have to use this different type of quantum walk.
Okay, I see. And sorry, and another earlier question for when you mentioned the heating time.
Yes.
Improving them in the expectation sense, right? So it means you are working under some distribution, either in the quantum case, the one quantum sample oracle. And is there any constraint for the distribution, or you just say for any general distribution you can prove this kind of result? Is there any? You have to assume you have the fully access to the distribution, right?
You mean pi?
Yeah, pi. Yeah, in the pi, yes.
So okay, so you assume that that you're given this as an initial quantum state, right? Just like classically, you're assuming that your initial state is somehow given as the stationary distribution.
Okay, so you are assuming you already have this state prepared for representing this distribution.
Yeah. Yes. So in many cases we can actually do that, but it is something that's a non-trivial cost. It's like in sort of abstract quantum walk search algorithms, what we call the setup cost, like the cost of setting up the algorithm. Like we want to start from this pi. So here we're in a slightly more abstract setting where we just assume that we have access to this, but there's ways of preparing this state, which in general should not be discarded. But here for like ease of exposition, in fact, in this full line of work, people typically assume that, okay, if we can start from this state, then can we get this quadratic improvement?
Okay, I see. Okay, thank you.
Okay, so any other questions?
I'm good now. Thank you.
Okay, good. So let me dive into a bit of the techniques then. Basically, what we want to do is we want to prove this sort of this continuous time analog of this quantum fast forwarding result. And so what the main technique here is a thing called a quantum Gaussian filter. And we didn't call it that. In fact, it's also not called like that in our paper. But afterwards, we learned that there's some concurrent work where they do something similar, and there they call it the quantum Gaussian filter. And I kind of like the name, so I'll use it, and I'll also mention the work where it was initially defined like that. So this quantum Gaussian filter is related to a concept called imaginary time evolution, which on its turn is related to ground state preparation. So for starters, when we talk about real-time evolution, we mean the sort of trivial thing, which I've already written down a couple of times. You go from psi 0 to some psi t, which takes the form e to the minus I t h psi 0 for some Hamiltonian h and real t. And this is typically what we call quantum dynamics. Okay, like this is what happens when you integrate Schrödinger's equations, what happens when a natural quantum system evolves. However, in many cases, we're not interested in the dynamics of the system, but we're interested in the ground state of a system, right? So if you plot like the spectrum of the Hamiltonian on an axis, then we'll assume that the smallest eigenvalue is equal to 0, and then we have a lambda 1 of h, lambda 2 of h, and so on in increasing order. And then there's this gap here, which we call the spectral gap. And so often we're interested in the eigenvector or eigenspace corresponding to this 0 eigenstate, and the complexity of sort of reaching this subspace or preparing this ground state typically scales inversely proportional to this spectral gap. So if it's small, then it's going to be much harder than if it's large. So given that we're often interested in these ground states, a typical problem is given some Hamiltonian H, prepare a ground state of H. Okay, so this is a very typical and generic problem. And a solution is imaginary time evolution. So what does that mean? We won't evolve like we did here, what we call real-time evolution, but we do imaginary time evolution. So what we basically do is we replace this time parameter t by minus it, so hence imaginary time evolution. So now the time is somehow an imaginary variable. And Hamiltonian evolution now takes the form e to the minus I t h. And this operator is exactly what we call implementing imaginary time evolution. And I'll show you why we're interested in that. Because basically, if you expand h in its eigenbasis, then this basically takes the form minus t lambda j of h, or lambda j is a jth eigenvalue, and then eigenvector vj, vj. And so now assuming for a second that the ground space is non-degenerate, then basically what we get is for t large, like all non-zero eigenvalues kind of get mapped to 0, and the 0th eigenvalue gets mapped to 1, and so we get essentially the projector onto the eigenspace. Okay, so this happens if t is much larger than 1 over delta. So this already hints at this complexity scaling with the inverse of the spectral gap. Okay, so if we're given some state psi 0, and we can assume that it has a non-zero overlap with the stationary, with the ground space, then what we get is that if we apply this imaginary time evolution minus ht on psi 0, then this gets mapped for t large to basically we take the inner product with the ground space, and then we get this ground state. So essentially, we prepare a state which is proportional to the ground space, to the ground state, which is what we wanted. And that is also why you could call this operator a filter, because somehow it filters out all the higher modes and it just keeps the ground state in there. Okay, so this is a very nice and simple idea. But of course, the key question is how do we implement this filter, or this imaginary time evolution? And notice that it is kind of similar to how a continuous time random walk operator looks. But what we can show is that in fact we can use like real-time evolution. So we can just use Hamiltonian simulation to implement this imaginary time evolution. And that's the content of this small lemma here, which says that for any t greater than or equal to 0, we can implement this operator, this imaginary time operator, e to the minus t h squared. So there's a catch here. So there's a square here, and I'll definitely get back to that. By integrating h, you just real like Hamiltonian simulation, for time scaling as the square root of t log 1 over epsilon. So this is in fact okay. We can, so I should put, we can epsilon approximately implement this imaginary time evolution of this filter by integrating h for time that scales as the square root of t. That's kind of the main thing here. Okay, so this is what we call as a quantum Gaussian filter. It'll become clear why it's a Gaussian filter. You can already see it basically from the form e to the minus something h squared instead of h. And similar ideas, again, were around. So some of the ideas already appeared in a paper by Chowdhury and Soma from 2017, where they described an algorithm for preparing Gibbs states. But it turned out, and this is the concurrent work that I mentioned earlier. So these are two concurrent works that we found out after, finished writing this thing. That there's a paper by Keen, Dumitrescu, and Wang, and by a paper by He, Zhang, and Wang, both from end of 21, I think, where they also use similar ideas for preparing ground states. So I also phrased this filter as a thing to prepare ground states, which is also the way they use this. But in fact, we will use it in a slightly different way, because we will actually use it to simulate dynamics rather than prepare a static, like a ground state or Gibbs state. So while this idea kind of showed up in these papers as well, we really used it in a different manner. Okay, that's essentially what I'm stating here. So different with respect to this work is that we use the filter to simulate dynamics instead of preparing some state. And as I mentioned before, there's this square here. So basically, what we show is that we implement e to the minus t h squared with a cost that scales as t to the 1 over 2. So we have this square here, and then we have this 1 over 2 here. And it's not completely clear to me why exactly we get this, but there is the sanity check that since the square here shows up, the Hamiltonian that we're kind of doing imaginary time evolution for now has a smaller gap, right? The gap is now the gap is now delta squared. Right? By taking the square of the h, the gap actually becomes smaller, and so we would have to do the imaginary time evolution for a quadratically longer time, namely 1 over delta squared. But then it turns out that, in fact, the cost of actually doing it for time t actually scales with square root t. Right? So what we get is that we should take t to be 1 over the gap of h squared. So this is 1 over delta squared, and to the 1/2. And so this, in the end, scales as 1 over delta, 1 over the gap. And this is really what we should have expected. If we would have gotten a better thing, then something should have been wrong, because there's sort of complexity type results that show that for certain Hamiltonians you cannot kind of amplify the gap. For many you can, but for many you cannot. And so this is like a good sanity check. And let me just walk through the main ideas a little bit of proving this. One is elementary Fourier analysis, or a thing called the Bose-Hubbard transform. So consider the function, basically a Gaussian e to the minus x squared over 2. If you Fourier transform this thing to some frequency domain, which with variable y, then we again get a Gaussian. So up to some proportionality factor, we basically again get a Gaussian. In other words, in a formula, this says that e to the minus x squared over 2, we can decompose it as a Gaussian combination of waves, essentially, right? So we have these imaginary so these complex exponentials here. Basically, we get that this Gaussian can be described as a linear combination of these complex exponentials, where linear combination is again basically a Gaussian. Now, as a consequence, if we just replace x by square root 2t times h, we get that e to the minus th squared is essentially equal to 1 over square root 2 pi integral dy e to the minus y squared over 2 times, and here it comes, minus I y square root 2th. But now notice that this thing here is just real-time evolution. This is just a Hamiltonian evolution. So what we see is that this imaginary time evolution can be seen as a linear combination of real-time evolutions. And this is kind of the key thing that we use. Now, where does the square root come from? There's a truncation that we can do because, in principle, this Gaussian, this linear combination extends to support from minus infinity to plus infinity, but we can truncate it. And in fact, we can get an epsilon error by truncating it at around plus or minus square root log 1 over epsilon. So basically what we get is that we get this linear combination, and now we just go from minus square root log 1 over epsilon to plus square root log 1 over epsilon of whatever was there before. And so then you can see that the actual time for which, like the maximum time for which we evolve the Hamiltonian h, actually scales as square root t square root log 1 over epsilon, which is exactly the parameter that I put here before. Okay, so this is just like some maths, but now as I'm sure it rings a bell for some people, now we want to implement this like linear combination of Hamiltonian dynamics, or basically unitaries. And so then you have this technique called linear combination of unitaries, which in principle I would not necessarily walk through because I'm assuming some people are already familiar with this, so there's not really much new here. But I kind of like that, and this is what I was referring to before, is that in this continuous setting here, it kind of takes a particularly neat form, and this LCU really kind of pops out very naturally, which I liked. So we want to implement this linear combination of Hamiltonian evolutions, which is no longer a unitary operator. So we'll have to do some post-selection at the end, which I'll go back to. And in fact, what we need is we have our primary system, which is where the quantum walk takes place. But now we'll have this smaller auxiliary system, like some ancilla registers, where we'll assume, for the sake of simplicity, that we have a continuous variable. That basically we'll be putting a Gaussian state in there, and you can discretize everything if you prefer. So as a state, we have some initial state, let's say chi0 in the quantum walk state space. So this could be the vertex or the vertex squared state space, something like that. And then in the extra auxiliary system, we put a state which is a Gaussian state. So basically, you can describe it as dy over now, because things have to square to a distribution. We get 2 pi to the 1 over 4 e to the minus y squared over 4y. This is a Gaussian state. And now we define a Hamiltonian on the larger system. So the Hamiltonian H prime, which is basically the quantum walk Hamiltonian on the primary system. And then this different operator y hat, which is, so here we have the quantum walk, and here this is basically what we call a position operator. So in continuous variable systems, and when talking about the harmonic oscillators or Gaussian states, these are kind of natural things, and you can just define it as the operator whose eigenstates are just the position states, y, like that. Okay, so again, I would like to, although this is not my expertise at all, but that these things are kind of all very natural in this more continuous setting. And if we define things like that, then what we get is that if we evolve for, let's say, some time t, this h prime operator, and we evolve a state psi y, let's say, so psi in the first register and just a simple y in the second register, then what we get, and this is not too hard to calculate, is that since y is an eigenvalue of y hat, with eigenvalue y, we just get a y here, and we get hp, and then we get psi. So what we see is what happens is that basically conditions on the second register will apply the quantum walk operator for time t times y. And this is very similar to how in LC you have a second register that tells you how many steps of the quantum walk do you do. And now, again, I'll leave it as a sort of exercise if you want. Basically, I should say it's just not so hard to prove, is that if you do this thing, and now you start from Gaussian in the second register instead of just y, and you have some initial state psi that you care about in the quantum walk register, you integrate this h prime operator, the coupled operator between the two systems, for time square root 2t, and then you look at what's in the sort of identity tensor Gaussian state subspace. So basically, you'll post-select on the second register being in the Gaussian state. Then what you get, and this is in fact not so hard to prove. Okay, it's just a one-line thing in our paper, but I try to be a bit sparse here. We basically apply this imaginary time evolution on our first register of interest. And so, okay, this operation here is basically what we call post-selection, and from a physical perspective, although I'm not completely confident what this means, this is basically what this can be performed by a thing called Homodyne Detection that basically allows you to do a measurement inside this basis of Gaussian states. And so you have the cost of implementing this operator here, and then you'll have an extra cost based on a post-selection procedure. So it might be that you have to repeat it a couple of times until you actually get the right state. But when you do, you get exactly the state that we're interested in, namely this imaginary time evolution applied to our system of interest. With that said, we can now kind of fill in the details. So this is what we call the Gaussian filter. So if you apply this for t, much larger than 1 over delta, then you basically get a projector onto the ground state. But we're interested in something slightly more refined, let's say, which is we'll care about this operator here, even for intermediate times t. Like we won't just care about its asymptotic behavior. And this is kind of a key thing. But first, what I wanted to mention is that we had mentioned this trade-off before, right? Between getting a square here, but then getting a 1 over 2 here, so that things kind of even out. But it turns out that, so I said that this makes sense because we can't amplify the gap for general Hamiltonians, but for certain Hamiltonians we can. And in fact, this is exactly what we did for the quantum walk, right? Because recall that we defined our quantum walk Hamiltonian as basically the following thing: n minus p squared psi 0. So if you'll believe me that this is kind of the transition kernel that we care about, so there's this p squared instead of p, but this really doesn't matter, then we get that HP is actually the square root of the type of evolution that we want. So we get access to the square root of the sort of actual Hamiltonian that we're interested in. And this is why we actually get a sort of gap amplification. And indeed, you see this by applying our Gaussian filter, because we basically get an imaginary time evolution of the form e to the minus t hp squared. And this is by this equation essentially equal to e to the minus t identity minus p squared. And this essentially corresponds to implementing a t time continuous time random walk in time that scales as square root t now, right? Because recall that we can implement this operator here in times square root t. Okay, so we can implement this t time continuous time random walk in something like square root t random walk, quantum walk evolution time, and this is what we'll call a continuous time quantum fast forwarding technique. Again, essentially, we implemented t-step continuous time random walk using square root t steps or square root t time continuous time quantum walk. And so here, notice that we implemented t-step continuous time random walk, right? We don't just implement like this sort of asymptotic operator. Like if you apply your continuous time random walk for a very long time, you also kind of project onto the stationary distribution. In many previous works, this was what we cared about. It's a bit like, we care just about the ground state, but here we'll actually care about this t-step continuous time random walk for intermediate values of t as well. And we kind of nicely, reproduce this evolution with this tool. And this is the key tool plus some more work. And here we largely use results from Ambainis, Gillian, Jeffrey, and Kokanis from 21, which also kind of have to be transposed to the continuous setting to prove this general quadratic speedup question for spatial search, which was a question that seems to have been open for some time, just like in a discrete time setting. Okay, and with that, I will start rounding up. So let me just, before I end, mention some open questions. So one of them is, I think is actually rather interesting, which is what are the limits of the simple continuous time quantum walk, where we don't have this larger coin operator and so on. And so it seems like there's, at least in discrete time, there's these sort of semi-formal results that show like a coin really makes the quantum walk stronger. So here this seems to be the case as well. But then, I mean, clearly this type of operator without the larger state space will be simpler to implement and is more elementary. And so really be interested in kind of probing what the limits are of this operator, because in fact, it often does give a quadratic speedup, right? And so I'm kind of interested in what the limits are here. And the second question is a bit more about, can we kind of prove a general correspondence between continuous time quantum walks and discrete time quantum walks? So what Childs did at some point is he showed that any continuous time quantum walk algorithm can be simulated by a discrete time quantum walk. So he proved this in a paper where he basically used this sort of correspondence to show that his glue trees construction can be implemented with discrete time quantum walks as well. But the other way around seems to be much less clear. And in fact, we were really like trying pretty hard to find this general correspondence, but we did not manage to. So I think this is like a nice open question. And with that, I'll conclude and I'll thank you all for listening and for the kind invitation to talk in your seminar.
Okay.
Thank you.
Thank you very much. I really liked your talks, especially I really appreciate like writing while explaining instead of like using slide. That I find that it's much easier to follow what you.
I think so. Right?
Yeah.
I think it's nice that if you give a Blackboard talk, then sometimes I feel it's a bit too slow. Like sometimes you want to just put a bit of text there and share it, and you can kind of do that.
Okay.
So
yes, thanks a lot. And I also got very interested into what quantum walk can do. So that's why Jim Guojin, he is also working on this domain, and even though we just started last year, so
okay.
there are so those reference that you mentioned, we have been reading quite extensively on those papers. For example, papers by Childs and also by Cizides. And so
Sorry, by who?
by this Caesardes. I think you mentioned his content works without like discrete.
Oh yeah, the Segedy paper. Yeah, yeah, yeah.
Yes, yes.
Yeah. Yeah, I mean, it's not an easy paper, right? But it's a very cool paper.
Yeah, and we are hoping to kind of like using those techniques for. I think we choose a topic on graph testing, relative
Like property testing.
Yeah, especially on graph testings. So maybe, yeah.
Okay. Okay. So in fact, I in this where is it? In this quantum fast forwarding paper, like this one here. In fact, we use this for some graph property testing problem as well.
Yeah. I think that motivated us. So we might bug you later on for further questions.
Yeah, please do.
Yes.
Please do.
Yes.
I think it's a very nice topic, right?
Okay.
So.
Yes. Okay. Is there any other questions?
Hello, I have a questions.
Yes.
I mean, you have mentioned that you could use this technique to prepare the Gibbs state.
So this was used.
Is it possible?
In this Chaudhuri-Soma paper, yes.
Yeah. Is there any restriction or technical difficulty to do that?
No, I think the idea is quite elementary. So basically, you have this imaginary time evolution. And I think the idea is that you apply it. So let's see, like so you want to do Gibbs state, right? So the idea is that you apply e to the minus t h squared to like the maximally entangled state, I think. Like you do something of the form, I guess, let's say x, but this is the same thing as you can rewrite this in the eigenbasis of h. So you get e to the minus t h squared sum vj, something like that. And then, okay, you see that you are kind of getting there, because then you get something from e to the minus t lambda j of h squared. So they assume also they have access to the square root of h. So this, I think, is maybe important. So that basically they kind of lose the square here, and then you get vj. And then I'm probably missing something, but then there's like one last operation that kind of performs a measurement, so that in the end you kind of map this to the density matrix rho proportional to jh vj like that. So it's kind of like, I mean, it's a bit of a trick, and in fact, okay, I'm missing a little part here that I don't directly remember, but other than that, it's kind of straightforward.
Okay, thank you. Is there any other questions?
Sorry, I'm just curious about the fast forwarding. Why it is called fast forwarding? What's the improvement over the previous one? Why it is called this name?
Wait, so I should. Or it's before it. So you mean why it's called fast forwarding?
Yes.
Okay, so it turns out it's not a great name, because there's these no fast forwarding results, and like in Hamiltonian simulation setting, it kind of means a bit of a different thing. But here it just means fast forwarding because we can implement t steps of a random walk with square root t steps of a quantum walk. So we get a we kind of implement a t step evolution in quadratically less time. Does that make sense?
Yeah, but if you apply the quantum setting, usually it's the square improvement. So what's the good thing? I mean, square root is common in quantum work setting. So why?
Oh, you mean you naturally get this quadratic improvement? You mean?
Yeah, I think in the quantum work, it's quite natural to me.
Well, okay. I mean, okay. I guess you can argue that it's not outside of expectation, like that it's possible. But I mean, at least to us, this was a priori not at all clear. Like, I mean, there's many things that random walks, can do, and that quantum walks cannot do quadratically faster. Like, for instance, there's this big open question of, use a random walk to prepare the stationary state, which is, typically in Markov chain Monte Carlo, like really the key task. This we don't know how to do quadratically faster with a quantum walk. I think this is, in fact, one of my favorite open questions here. And so this is something that we don't know how to do. This thing here, I mean, I hadn't been around before, and it turns out to be pretty useful. And I think it was completely clear that indeed you could do this. Like, in fact, okay, let me say just one more thing. Like, it is not even obvious that you can do this, because the classical walk and the quantum walk have the same locality, right? Like, basically in one step, at least in discrete setting, you can just jump to the neighbors. And so in principle, a random walk could, jump, go to distance t in t steps, whereas a quantum walk could not. It can just, in square root t steps, it can just move, square root t steps away. But it just turns out that random walks are so slow that they always stay within this square root t region, and hence in square root t you can kind of simulate their behavior. I think this is something that I kind of learned from this result. So it was not so obvious to me beforehand.
Okay, I see. Thank you.
And is there any other questions? Okay, I have another question. You have mentioned that you use the linear combination of unitary to create the imaginary time evolution.
Yes. Yeah.
Yeah, that means you have two post measure
Yes.
many times. And is there any constraint on the time of the post measurement, or?
Yes. So you can calculate it, right? So basically, the probability of success, if you look at this post selection, has a success probability which is equal to, like, if you just naively do the measurement, then you could kind of improve it by doing amplitude amplification. But naively, the success probability is exactly equal to the norm of e to the minus th squared psi. This would be exactly the success probability if you measure this state. And so you would have to repeat it 1 over this norm squared times. And in many cases, this can become really small, right? Like I already mentioned this mixing question before, where typically you start from one vertex, which has obviously one norm 1, but also 2 norm equal to 1. But then it goes to this distribution, which is a uniform distribution. But uniform distribution has a very small 2 norm. Like its 2 norm scales as 1 over square root n, the number of states. And so if you have to repeat this, like, so naively you could try to use this approach, but then you would have to repeat this n times, or square root n times if you use amplitude amplification. And that completely defeats the purpose of like in any Monte Carlo type algorithm, you never want anything scaling with the size of the state space.
Yes. So it is an important constraint. And in fact, the quadratic speedup for spatial time is also very useful. So you can, for example, use the linear combination of unitary to create the imaginary time evolution. And this means you have two post measure many times. And so you can,
a lot of effort in this unbalanced Gaussian Jeffrey cocainase result, and also in our result, is basically related to proving that the success probability stays large. So
I
for
see.
the search setting, if you start, and that's also why you need to start from the stationary, because basically it kind of has a nice spread, then you can keep the success probability large. Yeah.
Oh, I see. Thank you. Is there any other question from the audience? So, okay, so it's about time to finish this this seminar. So thank you, Simon, Apers again.
Okay, thanks a lot. Yes,
Yeah,
hope to see you
Thank you.
sometime soon.
it was a pleasure, and feel free
Okay.
to bug about the graph property testing. And
Yeah. We would definitely we would.
Okay,
Okay.
good.
See you
Take
then.
care.
Thank you.
Okay, bye.
Thank you.
Bye.
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 线上有人下礼拜想要进场吗？应该没有吧。